By now, you've probably heard that generative AI, like ChatGPT, was trained to fill in the blanks in phrases like this one: Mike is quick, he moves. As a human, you can read this and guess that Mike probably moves quickly. But how do you get a computer to fill in the blank like that? Well, here's a fill in the blank that you've probably seen a computer solve already. And in fact, we could make this problem a lot more complex. And this is still the type of fill in the blank that computers are good at. In essence, researchers have figured out how to map words into numbers, turning what is a word problem into a number problem. That mapping of words into numbers is called an embedding, and it's the subject of this video on understanding word embeddings. Welcome to Spreadsheets Are All You Need, where if you can read a spreadsheet, you can understand modern AI. That's because in this series, we're walking through a spreadsheet that implements a full large language model. And not just any large language model, but GPT-2, a model that was state-of-the-art just a few years ago and an early precursor to ChatGPT. If you're enjoying this series or find it helpful, visit the website Spreadsheets-are-all-you-nned.ai and subscribe to the mailing list to get notified of updates and new videos. So let's resume where we left off with this simplification of how a large language model is operating. Now, there's a couple differences. Instead of classic arithmetic here, we have the much more complex mathematical operations of the multi-head attention and multi-layer perceptron layers. And you can see this in the spreadsheet right here in these tabs, block 0 through block 11. We'll be covering this in more detail in subsequent videos. The key thing I want you to notice is that all this processing here is numbers. You don't really see any text at all. And another difference is, unlike regular arithmetic, the answer isn't precise, it's more approximate. And so it's interpreted as a probability for what the next token is by the language head. But before we can do any of that mathematics, we need to translate the words into numbers by using text and position embeddings. These text and position embeddings are part of the process that bridges the gap between the text you enter and the heart of the large language model that only understands numbers. The first part of this process we covered previously in the tokenization episode, and that's a process that turns text into tokens. The second part of this takes the tokens and turns them into numbers that we can do mathematics on. If you watched the previous lesson on tokenization, you might be wondering why we can't use these, the token IDs that we discussed in that previous video. The problem essentially is that the token IDs are identifiers, but they don't actually measure anything, and they don't group related words close together. This is easier to see graphically. Let's take a look in the spreadsheet. Okay, here in the spreadsheet, I've added those tokens: happy, joyful, glad, sad, happy with the capital H, cat, dog, and rabbit, all as a prompt, then ran them through prompt to tokens, which gives us our token IDs, updated the constants, and then went to the tokens to text embeddings tab. We're going to ignore the embeddings for now, and I just want to grab the tokens and their token IDs. I'm going to copy this. I'll create a new sheet. And then I'll paste these by value. And then I'll just give these all the same Y value. My charts. And highlight the data. Insert a scatter chart like that. I'll expand this out so it's easier to see. We'll add some data labels, and then we'll configure those data labels. Right here with the value from cells for the labels. Hit OK. There we go. And we don't care about the Y value, but we do care about the X value just for illustration purposes. Now you'll notice they're all bunched up here, so let's move these around so they're a little easier to see. So there's happy. Let's move sad over here, glad over here. And then here you notice we've got happy and cat are really close together, 3772 and 3797. And then dog is also very close to it, 3290. Meanwhile, if we take a look at the synonyms of happy, so here's happy right here, the word glad is a lot farther away than cat is to happy. And happy with a capital H, which basically should mean roughly the same thing, is over here at 14,628. Even worse, joyful, which is a synonym, is all the way over here at 48,977. It's really far away. And so the problem is, if we're doing math and approximate math on these token IDs, and I get happy slightly off, so instead of 3772, I end up slightly to the left or slightly to the right, I want to actually hit the word joyful or glad. I don't want to accidentally hit the word cat or dog, or that would get me completely the opposite meaning of what I'm intending. We'd like the related words to be grouped together in roughly the same spot on the graph. Now, the reason this happens has to do with the BPE or tokenization algorithm. If you recall from the earlier video, the way the process works is by identifying merges with the most frequency and gradually building up a vocabulary. So in essence, the vocabulary lists the words in decreasing popularity. So the reason, for example, that happy is got such a small token ID, 3772, and joyful has such a larger token ID, 48977, is because happy is a much more common word than joyful. That's why dog and cat and sad are so close together, but yet glad and happy with a capital are further away from it. Now, another problem with using a single number to represent a meaning of a word is that words can have multiple meanings. So as we've talked about, this word quick, in our example, Mike is quick, he moves, can mean moving around in physical space. It can mean bright, as in quick of wit. It can be a body part, as in the quick of your fingernail. Or it can even mean alive or dead in Shakespearean English. And so having a single number represent all these different meanings that a token or word can have is challenging. Further complicating matters is that a token can be present by itself or sometimes as part of another word. So take, for example, quick. It can be by itself, as in the word quick, but it can also be part of the words quick lime or quickening. This further challenges the idea of having a single number represent the meaning of this token. Another challenge is that the tokens themselves may represent concepts that are not directly comparable. So for example here, the first 5 words or tokens represent emotions: happy, joyful, glad, sad, and happy. And the last 3 are animals. It's not clear mathematically how we would relate these two. So if one single number isn't sufficient to represent a word or token, maybe we need to just add more numbers or dimensions to represent the meaning of each token. These are the embedding values, and the number of columns is the number of embedding dimensions. Now, don't let this word embeddings scare you. You're probably already used to multiple dimension data all around you. Let's suppose, for example, you're looking for a house to rent. Well, the addresses are kind of like our token identifiers. They'd tell you where to find the house. But what you're really interested in are the features of each property. So its square feet, its number of bedrooms, its number of bathrooms, and its price. Those would be like our embedding values. The difference between just plain tabular data like this and an embedding is that in an embedding, there's a mathematical relationship between each of these rows and where they sit inside the embedding space. Let's use a simple two-dimensional example. So suppose we take the token man, and we're going to have a two-dimensional embedding where one dimension is authority, and the other dimension represents gender. So we'll assign for man authority of 1 and a gender of 1. For a woman, we'll assign authority of 1 and a gender of 2. For king, we'll give it more authority, so authority of 2 and a gender of 1. And then for queen, we'll give authority of 2 and a gender of 2. What we've basically done is created a embedding space of 2 dimensions, and we've embedded each of these tokens inside that space. as you can see here. So for example, queen with authority of 2 and gender of 2 occupies a position 2, 2 in this coordinate plane. Now we can actually begin to do mathematics on these tokens in a meaningful way. So if we take king and we subtract man and we add woman, then what we end up with, if we add it all together by adding and subtracting around each of these columns or dimensions, so 2 minus 1 plus 1 will equal 2. And then if we do the same thing for gender, 1 minus 1 plus 2 is equal to 2. And what we see is that this 2, 2 is actually the same value as queen. In other words, king minus man plus woman equals queen. This is a very famous result in natural language processing, and we can consider it like an analogy. King is to man as queen is to woman. And we can actually look at this as a fill-in-the-blank problem. King is to man as blank is to woman. It's our first fill-in-the-blank that we can solve with math. This ability to capture word relationships or analogies goes beyond just kings and queens. One of the most celebrated word embeddings, known as Word2Vec, was able to capture a wide variety of relationships. For example, here we've got capitals. France is to Paris, as Italy is to Rome. Or Einstein is to scientist, as Messi is to midfielder. Or Japan is to sushi, as Germany is to bratwurst. Clearly, Word2Vec was able to understand something about the meanings of these words and relate them together. In practice, real-world embeddings are different than what we've described here, though. Real embeddings have many, many more dimensions or columns. In fact, they typically have 100 to over 1,000 dimensions. In the case of GPT-2, there's 768 dimensions. We can actually see this inside the sheet. So here we are in the sheet and the Tokens to Text Embeddings tab. In the first column, we have the tokens from the prompt. In the second column, the token IDs. And then from column 3 onward, these are the embedding values for each token. And you can see it starts here at column 3 and it extends for 768 positions. So go to 770, which would be 768 positions. And we can see it basically ends right here. Another difference is that the columns are not directly interpretable. In the hypothetical two-dimensional example, we said the first column represented authority and the second column represented gender. But in real embeddings, we have no idea what each column represents. And in fact, they're probably not representing any single thing. And similarly, the values themselves are not directly interpretable in the way that we were doing in our king, queen, man example. So it's a little bit like in our housing analogy, if someone basically removed the labels at the top of the columns. This would still be useful information, though, if we were house hunting. If, say, I went to 47 Ivy Lane and I really like that house and I want to know what the other houses like it might be, I'd know from this data that 58 Sun Ave and 15 Luna Lane would actually be very similar based on looking at the values in these columns. I can see that the first column has about the same value. They're both in the, or all three of them are in the 2400s. And then for the remaining columns, they all have 3 right here, right here, right here in this column. And then in this column as well, 3, 3, 3. And then also their price, or, well, I don't know what the units are here, are all the same. So even though I don't know what these column labels are, I'm able to relate things that are the same by just simply comparing their values in the columns. So let's take a look at the Token to Text Embeddings tab inside the spreadsheet to better understand how the tokens are converted into their embedding values. So here we are in the Tokens to Text Embeddings tab. The first 2 columns are really just repeating the data from the previous tab. So over here in Prompt to Tokens, we have the results of the tokenization algorithm. So you can see here, we have the final token list, and we have the tokens to IDs. And if you go to Tokens to Text Embeddings and you look at this formula, it's really just grabbing that last row from the prompt to tokens tab and just simply transposing it and inserting it right here. Same thing for the prompt to token IDs. For the token to text embeddings, actually all the hard work has been done for us during training. We really just need to pull it out of effectively a dictionary that's sitting inside the spreadsheet. Inside the spreadsheet is a matrix called model_WTE. And this matrix has 768 columns for each of the embedding dimensions. And then it has 50,257 rows, one for every single token in the vocabulary. And so every token has its embedding values essentially in this row. So if we wanted, for example, the embedding values for the word dog here, we just grab the row for dog and just copy those values over. And that's all we really need to do. If you look at this formula, you can see what it's doing is there's a little if statement to catch if there's some blank data here in the previous column. Other than that, it grabs the token ID and looks up the effective value in this model_WTE matrix, which we can go take a look at. So here's the model_WTE matrix. It's really large. It's one of the largest weight matrices in the spreadsheet. And you'll notice it's got 768 columns. So if we go to the 768th column and then just go a few over, you can see that's where it ends. So this whole row, which is row 2538, is the embedding values for the 2538th token in the token dictionary. And so we just simply need to pull out what the token ID is, go to the appropriate row and pull that one out. Let's see that a little bit more detail. So let's go back here and go to tokens to text embeddings, and we see 3772. So let's go take a look at that row inside the matrix. So we'll note this 0.089. So if we go here and we go to back to WTE and 3772. So let's go to row 3772. Let's go to the first column. And there it is. And we are off by 1. So 3773. And you can see 0.896. So that's the first value we saw here that we saw back here in tokens to text embeddings. You can do the same thing for each of these. We're basically just pulling that row out of the matrix and dropping it in here. So after all that discussion about conceptually what an embedding is, in practice, using it is really simple. You just go look up the token's embedding value in a dictionary and just plop it into the right part of the spreadsheet. Now, while we're here, there's a few things I'd like to demonstrate. The first is that these embeddings do a better job of grouping the tokens that are similar closer together than we saw with the token IDs. So to do that, I'm going to copy the tokens with their embeddings. I'll create a new sheet, and I'm going to paste those in by value here. And then rather than having the token IDs in here, what I'm going to put is the distance to happy. And I'm going to measure for each token how far away it is from this happy token based on its embedding. So one thing to note is how we measure distance in an embedding space. You might expect that we just simply look at the conventional distance or Euclidean distance between 2 points. It turns out in a high dimensional space, distances tend to accumulate in a less meaningful way than you would expect. And so there are a lot of other ways to measure similarity. One of the more common ones is something known as cosine similarity. And the way cosine similarity works is it measures the angle of the vectors between the 2 points and how big that is. You can think of this as basically saying how close they are pointing in the same direction in space. And cosine similarity varies from -1 to 1, where 1 being very similar, 0 being unrelated, and opposed being -1. This sense of opposed is not opposite in the conventional sense that you might expect. So happy and sad won't get necessarily a negative value because even though they might be opposite emotions, they're still very similar in a lot of other properties. They're both emotions, for one. So it's more common that if words are not related to each other, you'll get a 0 value, then you'll find you get a negative value. I've added a named function to the spreadsheet for cosine similarity. So we can just do cosine similarity. Whoops. Cosine, there we go. And just give it 2 ranges, and it'll give us the cosine similarity between those 2 ranges. So let's do row 2, which is the current row we're in for happy. And then starting with column 3, going to row 2, column, so I put column, there we go, column 3. Then 2, column 770, and then we'll do the relative, which is this one right there, to RC 768. There we go. So that gives us a similarity of 1, which is exactly what we expected, since happy should be completely close to itself. Let's see how close all these other ones are. So copy and paste this formula, paste it down, and then we have to calculate sheet. And here we can see, and actually we can just do this right now. Let's add a new column. There we go. And we can plot these again as a scatter plot. Insert chart, scatter, and then let's expand this out so we get a good look here. Add our data label. Let's go back here. There we go. Label options, value from cells. Here we can grab the labels. And then we don't care about the Y value, we care about the X value here. Okay, now we can see more graphically how it looks. So we can see that as expected, once I put these out, there's joyful. All right, and here's cat, here's rabbit and dog. So we've got happy right here at 1. And what you'd expect, happy with the capital H is right here at 0.6, which has basically the same token as this happy, it's just uppercase, is the closest token to our original happy. Glad, joyful, and sad are all synonyms. Sorry, sad is not a synonym, so it's further away than joyful and glad are. But it's closer because it's also an emotion. So you'll see that it's closer than, say, cat, dog, and rabbit are, because it is more of an emotion and relatable than dog, cat, and rabbit. And those are the furthest away. So this is basically doing a better job capturing similarity than the token IDs were doing. And as we'll see in a little bit, it actually does a lot better clustering them when we have another way to look at it called PCA. So let's look at this data using PCA. That stands for Principal Component Analysis. And what it will let us do is take these 768 dimensions and squash it down to 2 or 3 or some smaller set of dimensions that are easier to visualize. And we can do this by taking our tokens here along with their embeddings. I'm going to copy this. And once again, I'm going to create a new sheet. And I'll paste it in by value. And we're just going to get rid of the token IDs because we don't need those. So here we have basically our tokens and their embeddings. Now, the bad news is you can't generate PCA in standard Excel without at least any add-ins, but it's very easy to generate inside Python. So I'll take these rows of data, I'll copy them, and then I happen to have a Python file over here. It's just basically less than 40 lines of Python that will take an input data file and turn it into a PCA graph. And I actually didn't even write this. I asked ChatGPT to write it, and this is what it popped out. So I'll put my embeddings here in this TSV file, hit save, and then we'll just run this. Okay, so here is the 2D PCA plot of the embeddings for the tokens we've been studying for a while now. So as you notice, happy capitalized and happy lowercase, both are very close to each other, as we would expect. Glad is very close to them, so is joyful. So the synonyms are grouped together nicely. Sad is not right next to them, but it's closer than, say, dog and cat and rabbit, which are animals. So you can see that the embeddings are doing a decent job grouping related words together than we were doing just using the token IDs. And we'll see this in much more detail with a lot more words in a little bit when we talk about TensorFlow's projector. Another fun exercise using the spreadsheet is to recreate the king minus man plus woman equals queen using functions in the sheet. So let's see how we can do that. So let's go over to our prompt, and we're just going to put in those words. So I'm going to do king, man, woman, and queen. And notice I'm putting in the spaces because that's common with the tokenization algorithm in GPT-2. I will go over to prompt to tokens and go to our formulas and calculate sheet. And now I can go over to constants. I'll run that. This will update the number of tokens. And then let's go to our token to text embeddings. Okay, now we can see our tokens, king, man, woman, queen, and then their text embeddings. So let's subtract king minus man plus woman. So king minus man plus woman. And we'll overwrite the formula in the sheet. That's okay. So king, this, minus this, plus this. And we'll take that and we will select the range R7 to C770 and then paste it in. And then we'll just calculate sheet. Okay, now you look at this and you're like, well, this doesn't look exactly like what I see up here. But remember, we need to look at this in terms of cosine similarity. So let's take the cosine similarity of this against queen. So similarity. I don't even remember how's this spelled. There we go. Similarity, queen, and king minus man plus woman. So cosine similarity of this range going to C768 in this case, since it's relative, and then this range. Okay, 0.7. Remember, 1 would be dead on exact. 0.7, as we've seen, is pretty high. It's actually higher than some of the other tokens we were looking at. We can actually go further and take a look at what all the other tokens are that could have been candidates that are close to king minus man plus woman. So let's jump over to that sheet and take a look at that. Okay, let's do the first row. And let's go to column 770 inside the weight matrix for the text embeddings. So what we want to do is we want to take each one of these, because they each represent a token, and compare it against king minus man plus woman. So we're going to do cosine similarity of this row, and we'll do on this row column 1 to this row, column 7, relative, RC1 to RC768, which is that entire row here. And then we're going to compare it against, back to our sheet, tokens to text embeddings, and we're going to compare it against this range here. So this all the way to R6, R7. I'm going to make these absolute. R7, C3, R7, C7, 7. And that should give us, double check this. There we go. Now I'm just realizing that this cannot be absolute. This is going to need to be, no, it can be. My bad. Okay, so let's take this, copy, paste it down. Remember, we have to calculate sheet. Okay, it's working. Let's take this, whoops, copy this, and then R1, C770, and then remember there are 50,267 rows, if I remember that correctly. So actually, let's go take a look. Row 50,267, C770. There we go. So we want to go from here back to row 1, C770. Highlight that area, and then paste. Okay, now calculate sheet. Okay, so now we have every token known in the GPT-2 vocabulary compared against king minus man plus woman. Now what we want to do is find out what the highest values were. So let's take the formula large, which will give us the largest values in an array. We'll just select this array, and we'll ask for the first one. We can also ask for the second and the third one. So we'll just copy and paste this down. Two, 3, get the first 5, 4, 5. Okay. Now we see, remember this 0.7085? That is what we had before for queen. There's a mystery here. There's one token that seems to be more likely than or closer than this one is. Maybe you've already guessed what it is. You see that 0.77? So let's figure out which token that is. So we can do that by constructing the reference to this token. So let's do a match. Look up this value inside this array, and the match type we want to be exact, so 0. And these are the token IDs, so 5823. Let's see what this one is. And we're going to get the repeated value simply because we need to calculate sheet. You can see them all adjust. Okay, next we need to figure out which token this 5823 is, and all these others. So we'll just do a reference to that particular token inside, you may remember, the sheet BPE to token IDs right here. And this has each row, so token 2565 is right here. So we just need to construct a reference to the right cell based on the row number. So that looks like this. We do BPE token IDs, row number comes from here, and the column is just always going to be 1 as a string. There we go. And then copy that. Calculate sheet. And you can see these are basically cell references that'll tell us which token each of these IDs are by their row. Let's do that. So indirect of this string and hit fall. There's king. And then let's just copy and paste this down and calculate sheet. Okay, so what we notice is that king minus man plus woman actually is closest to king. It's closest still to itself than it is to anything else. But the next closest thing is queen. And then you'll notice these other ones are reasonable. Princess, queen, very similar. Queen with capital, and then kings. So The funny thing about this famous result, king minus man plus woman equals queen, is something they don't often tell you, is that the algorithm that was used for that result intentionally removes the original word or any of the three words that were used in the equation. So king minus man plus woman, they exclude king, man, and woman. I'll go back here to make this more visual. The algorithm excludes king, man, and woman from its similarity search to pick the next closest item, or the next closest token, I should say. And that generally works well. So really what the math is doing is it's not necessarily landing directly onto queen. What it's doing is it's pulling the king vector closer towards queen, but not necessarily all the way. So the slide that I showed earlier where the points landed directly on queen isn't exactly happening. It's more like it's getting pulled closer to it, but it's still closer to itself. So with that knowledge, I encourage you to play around and experiment with trying a bunch of tokens, comparing them against themselves, doing analogies with math on them like you've seen here that you can do right in the spreadsheet without having to know any Python, and comparing them to some famous results. By now, you're probably wondering how the embedding values are actually chosen. The somewhat unsatisfying answer is they're just learned by the computer during the training process. So the training process consists of taking text from, say, the internet or books or a variety of other sources and taking words out and then asking the large language model to predict the completion. And when it gets it wrong, like in this case here, if it says he moves bicycle, then the algorithm known as backpropagation adjusts all the weights, whether that's inside multi-headed attention or inside the multi-layer perceptron, but also the embeddings themselves, such that when we try this phrase again, it hopefully gets it right. It says he moves quickly. And one thing to note is that it's doing this not just for this one phrase, but for a large number of phrases. And one advantage here is we actually don't have to have a human label all the data. We can do this entirely automatically, or what's called unsupervised learning, where a human doesn't really have to get involved in labeling the good and the bad examples. Now, even though it isn't entirely precise, we can develop some kind of intuition for what the training algorithm is doing. And that is, it is learning the word meanings by understanding them through their different statistics, how frequently they occur. So let's take, for example, the words ice and steam. So you might have phrases like this in our training data. It was so cold, the puddle had turned to ice. We put extra ice in the cooler to keep the drinks cold. You're as cold as ice. And then for steam, we'd have phrases like this. Steam rose from the still hot cup of coffee, and so forth. And what you'll notice is that the word cold and ice typically are occurring close to each other. Similarly, steam and hot are occurring close to each other. So what the algorithm can determine is that if it looks at ice, steam, cold, and hot, ice and cold occurs more often and steam and hot occur. So in essence, it's possible for a learning algorithm to understand that ice is cold and steam is hot just by looking at a wide swath of text on the internet. And there's a famous phrase you'll often hear folks refer to in the natural language processing space and AI space. You shall know a word by the company it keeps, from J.R. Firth. And it's basically saying you only really know what the definition of a word is in its relation to other words. Essentially, the context that the word occurs in tells you what the definition is across many, 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 many sentences. So if you analyze enough of those many, many, many sentences, it is possible for an algorithm to understand the relationships between those words. One interesting way of visualizing this is with the TensorFlow.org projector. You can select between a variety of different embeddings. Here we're using the famous word-to-vec embedding, and we can actually visualize the embeddings inside a three-dimensional or even a two-dimensional space. We're using a technique called PCA, which basically projects all the dimensionality of the word-to-vec dimensions into just three to make it easier to see. So if you just click on this, so let's click on the word shaped, we can see triangular, rectangular, resembling, covered, hollow, circular, are all words that are similar to or close to the word shape. So let's just try one more example. Let's rotate this around and let's just pick this word. Ooh, I think I saw monster. Oh, there it is. Let's see what's close to monster. So creature, robot, Frankenstein, dragon, Godzilla, these all make sense that they would be close to monster in the embedding space. So this is a fun little visualization. Highly encourage you to check it out, projector.tensorflow.org. Now, before we leave embeddings, there are a few other concepts that are worth calling out. The first is retrieval augmented generation. This is a popular technique right now for dealing with large sets of data and making them available to large language models that haven't been trained on them. And it relies on this technology called a vector database. You can think of this as a database that's specifically designed for storing and retrieving embeddings, such that you can query the database for the embeddings that are close to another given embedding. And you start with this vector database and you pass it a large collection of documents. So for example, you might pass it all the pages of your product documentation. And then a user comes and enters a prompt. So maybe there's a customer support request that comes in, and it is fed to the vector database, which goes and looks up for all the documents that are close to the request in the embedding space. Essentially the ones that match it is in cosine similarity, for example. And so you get a list of relevant documents. So it might be the pages of documentation that talk about the same concepts that the customer support request is asking about. Then you combine the user prompt and the relevant documents together. So in this case, you would take the customer support request and the relevant documentation pages, and you would pass those together to a large language model. And the large language model then would send a response back to the user. Effectively, this lets the large language model incorporate relevant data that it was not trained on. So it can answer the question based on the relevant pages of your product documentation, which probably weren't in the training data. Now, it's important to understand that in retrieval augmented generation, you're usually not using these text and position embeddings right here, which is the embeddings we've generally been talking about at the beginning of the large language model process. Instead, what's done is you rip off the language head at the very end and you take the last output of the last layer of the multi-layer perceptron and you turn that into an embedding that represents the document or a chunk of the document. And the reason you do that is because the embedding that comes out of here, or the vector that comes out of here, has gone through the large language model process. So the context and relationships of words has been incorporated into this embedding. So you can think of it like Mike is quick, he moves. If we just took that out of here, it wouldn't know that this word quick refers to movement in physical space. It could be quick as in quick and the dead, or it could be the quick of your fingernail. But once it's passed through this whole process, it's been refined such that this value of quick and how it gets incorporated into the entire phrase knows that it's likely the one for physical space. So that's why we pull this as the embedding chunk and not right here. In the previous video, we talked about how tokens can be text, but they can also be images or patches of images. The same thing is true for images and embeddings. And in fact, you can put text and images into the same embedding space. And that's what this famous algorithm CLIP from OpenAI does and became the basis for a lot of those text-to-image tools you're probably familiar with already. Basically, by putting text and images into the same embedding space, we can pass it an image and it can give us text about what's in that image and vice versa. Finally, the last kind of fun treat I want to show you is this project from Brian Lowe and Tom White. And a shout out, by the way, to one of our readers who brought this one to my attention called Spacesheet, which is an interactive spreadsheet exploration through the latent space of an AI model. Let's go check it out. Now, technically, this is not a transformer-based embedding. This is actually going through something similar called the latent space of a generative adversarial network model, but let's ignore that detail for now. Basically, it lets you compare images in a spreadsheet interface around the embedding space or the latent space that generates these images. So let me show you this, for example. So I will let's take this guy here, and let's take this guy here. He's smiling. So let's add him here. And then let's take the difference between them. So minus this guy, minus that guy. And we get this face, but we can see there's a smile there. Like, these are all the characteristics of this image subtracted out of this image. And we can then take some other image, like let's take this guy right here. So let's take him. And then we can add to him this guy plus this weird delta vector between the smiling guy and the non-smiling guy, but we've got the smile. So we'll add that, and then we sum it together. And we have taken this guy and we've made him smile. We've made him actually a lot more similar to this guy than he is to that guy. You could take this guy who's also smiling. It's a fun little change. So we take him and we change it to this guy with glasses. And you can see it changes it a lot more dramatically. In some cases when I've done this, I've been able to get it to pick up on not just the smile, but the glasses. So this is a fun, very intuitive, graphical way, because humans are very visual and very facial oriented, to play with and understand what it's like for a embedding space, or rather a latent space here, for images. Okay, so that's text embeddings. Now, we have not covered position embeddings. We'll get to that and the rest of the GPT-2 architecture in subsequent videos. And in the meantime, if you've enjoyed these videos, please like or share it on your favorite social media platform. Thank you.